Theoretical versus experimental probability, that's where it's at. Okay, so the main difference is that when it comes to experimental, we base it on what actually happened, the trials. When it's theoretical, we do not care about what happened. We look at what is actually possible, right? And how many favorable events are there in that out of these possible outcomes. That's the biggest difference. And they will not always be the same or even similar. And what's the main reason for them not being the same? Because theoretical is what we're after, but it has to do with a small sample space, right? If you just roll the dice 4 times, so let's keep track here. I got a 4, a 5, a 4, and a 3, right? So out of 4 rolls, don't write this down, right? I'm just using this for, out of 4 rolls, I got a 4 twice. So technically that's half. So half of the time I'm going to get a 4. That's what the experimental probabilities tell me. It's wrong, right? We know it's 1 in 6. There are 6 possible outcomes, and it should be 1 out of 6. So I need to increase the number of rolls. Probably 50, right? 70, 100 times. And then you're going to start seeing similarities, right? You'll be off by a little bit, but if you go to 1,000 or more rolls, then they're definitely going to be very close to being the same. So that's the main problem when you're comparing the two. Okay, so let's give this a try. Page 29 here. Flipping a coin, right? Heads, actually, that would be heads. Heads and deer, right? Reindeer. Heads or tails. So George flipped a coin. Here are the results, right? 160 times it landed on heads. 240 times it landed on tails. Morning. Page 29. State the theoretical probability that the coin lands on tails. Theoretical probability of tails. Everybody loud and in unison. What is it? Thank you. Half, right? Which is 0.5, which is 50%. In theory, there are 2 options, right? One of them is tails, so it's 50%. The experimental probability on the coin landing on tails is different. Now we look at the experiment. We go up here. These are the results, right? It's trials, right? So the number of trials, if you add this up, 160 and 240, right? That's 400. 400 trials based on this. So we are going to have a 400 down here, and it landed on tails 240 times. Okay, so I'm going to write down trials. Landed on tails, right? Landed on tails. So we're emphasizing that it's what actually happened. And you can tell that it's not going to be half, right? 240 divided, that's 0.6 actually. Right, that's 0.6, which is 60%. So it's not adding up. Right? If you toss the coin 1,000 times, how many times would you expect it to land on tails? You're making a prediction. And I think it's safe to say that we would all agree that half of the times, or 500 times, we're expecting it to land on tails, 500 times or so on heads, right? So when you have both probabilities, always use the theoretical, always. If you only have this one, then right, blood type, that type, those questions where they did a survey or a poll or whatever, you have to base it on what you have, right? Not the theoretical. So here's 1/2 times 1,000, and so that'd be 500 times. Sorry. And so this is the theoretical, right? Theoretical probability. Okay. To make predictions, we use the theoretical. Let's do some cards here. Megan draws 5 cards from a standard deck of cards. So we know that's 52 we're talking about. Every time she pulls a card, she records the results and places it back. Right? State the theoretical probability of drawing a 6 of spades. Theoretical. So in theory, 6 spades. That's what I'm going to write down there. We know that in theory, we have 52 different options that we can draw. 6 of spades. How many 6 of spades? There's just one, right? Because you're down to just spades and there's only 1 6 in there. So that's what you're after there. Leave it like that, right? State the experimental probability of drawing a 6 of spades. So, okay, now we're going to base it on the experiment, on the trials, on what was recorded. So we drew 5 cards, or Megan did. Okay. And 6 of spades showed up twice. That would be 2 divided by 5 is 0.4, which is 40%. In this case, I will also find the decimal and percentage of this. So decimal gives you 0.0192. Multiplying that by 100 gives you 1.92%. So there's a very small chance of that happening in theory, but because there's such a small sample space, it just happens that there are 2 6 of spades there. Okay, so they're different. Why are the answers different? Which one is going to be more accurate in the long run, right? The experimental probability is misleading or biased due to the low sample space. Sample size, sample space. I didn't use space, right? So let's just stick with sample size. It is the same thing. If I ever do talk about sample space, it's the same thing. Okay, due to the low sample size. Okay, Megan should base her prediction on the theoretical probability. In the long run, the theoretical probability will be most accurate. There are certain things we do not want to use the theoretical probability. There are certain things like blood type, for example. If there are like, I think 7 or whatever different types of, I'm not going to say, oh, I think you have 1 out of 7 chance of being B+. I'm just going to give you B+ if you need blood. That's a terrible decision to make. But you actually want to make sure you check the blood type and you're not just going to go by probability. And in fact, when you do record the results, the experimental probability is the one you want to go by. That's really the best way to predict what blood type is most common, right? You base it on the results. You wouldn't just base it, but because it's not quite as random as cards, for example, right? Or rolling a dice. It's not evenly distributed. So 29, I'm done with that. So I told you I was just going to do a couple. I also want to take you all the way there's a blood type question. I did that on the key, but all the way to 36. I don't know, some of you may have actually checked this, right? But this is just talking about the importance of a sample size, right? And page 36, this is page 36. So we want a large sample space, large sample size, right? That's key to be accurate when you're collecting data and you want to make prediction. You want to have a large sample and diverse, right? So the size of the sample and how diverse it is makes a difference. You don't want to just ask in a specific area of Canada. You don't want to just go to Quebec and ask people there who you're going to vote for, because it's a totally different, almost like a different culture. It's like a country within a country, right? So you would want to diversify, go to different cities all over Canada and get a diverse sample so that it's not biased, right? These two things will avoid bias, right? Meaning that you're going to favor one over the other, right? So there's way more that goes into polling, to be honest, but that's beyond the scope of this course. But those two things are key to avoid a biased. So let's talk about, for example, here on 36, the full answer, you will have to go to the key, right? But over here, 36, the second question. You're in Vancouver, BC, and Katja conducted a survey in her math class and found that 29 out of 30 students have brown eyes. So therefore, she concluded that approximately 97% of the population of Canada has brown eyes. There's two things that are wrong here. First of all, the sample is very small, right? If you compare it to 35 million or so Canadians, and you just take 30, the sample size is too small. You just need to make a note of that, right? Low sample. I go in greater detail to explain that in the key. And what else is wrong? What could be potentially wrong with that? They tell you that it's just a math class, right? And actually just in Vancouver, right? So sample is not diverse enough. Right? I would say only one math class. Sorry, class. Only one city, right? So it should be many cities and not just a math class, right? Maybe, right, a couple hundred math classes, and then you would know. It's like you're going to an optometrist and asking optometrist how many people wear glasses, and you just base your answer on an optometrist, right? They would basically have almost 100%, right? Not quite, but if you go to an optometrist, that means that you probably need glasses, so it'd be a bad idea to collect your information and base it on that, right? So you don't want to be biased. Okay, AC time. Okay, so what's next, you might ask? We're going to do more after the AC, but now you should be comfortable with theoretical